Hello, welcome back to ECE 492 class. Following previous chapter, in this chapter, we will learn how to find the optimal synaptic weight and the bias of the perceptron through the least mean square method. The goal of this section is learn how to design a multiple input, single output model of the unknown dynamic system by building it around a single linear neuron. In another word, the goal of this section is finding the optimal synaptic weight, W, using the given training data. This is a simple single neuron perceptron model we learned from previous chapter. Here, input are x1 to xm with weight w1, w2 until wm. And here, we also have an extra input b, which act as the bias, and its weight is W0. So in previous chapter, we set W0 equal to 1. In the neuron, or we call it the processing unit, all the inputs multiply with its weight, and the products are then summed together. As we introduced in previous chapter, here, our goal is finding the optimal weight and bias so that the single neuron perceptron can perform its basic function in separation or classification. For this extra input b, it multiplied by 1 and then sum with other product in the neuron. We need to find the optimum b. Alternatively, we can set b equal to 1 and weight equal to W0. So, finding the optimum b problem becomes to finding the optimum W0 problem. Overall speaking, now the original input to the perceptron becomes to 1, x1, x2 until xm, and the weight is W0, W1, W2 until Wm, and our goal is finding the optimal weight vector. So in these slides, we'd like to introduce some basic terminology. First, the input vector x. It's also can called as the regressor. The weight vector w. That can be called as the stochastical environment. And D, that's desired output. As we learned before, we call that one desired response. The goal of the least mean square method is adjusting weight vector W0, W1 until Wm through an iteration process. In the iteration process, the output of the perceptron is calculated with the input vector and the current weight vector. The output is then compared with the desired response, and their difference is called the error. The error vector is then used to adjust the weight. This process repeats until reach the last training sample. Okay, before we introduce the least mean square method, we first learn some useful notation, which can make our equations easy to write and easy to understand. First, we're using capital X, to represent input vector, that is 1, x1 until xm. So here we're using the lowercase x to indicate each element. As we know, capital X is a m plus 1 by one vector, which means it has m plus 1 rows and only one column. We call that one is a column vector. Its transpose xt becomes a 1 by m plus 1 vector, which means it has one row, only one row, and m plus 1 column. We call that one as a row vector. Similar, we use in capital W to represent weight vector, and WT to represent its transpose. It should be noted that capital X and capital W, capital XT and capital WT, they have the same dimensions. So, in the neuron, the V equal to the summation of all products of X and W. Here, V is a scalar. We also can write it as a vector multiplication format, like here. That is capital X transpose multiply capital W. Here, as we know, capital X transpose is a 1 row by m plus 1 columns vector, and W is a m plus 1 row by 1 column vector, and their product V is a scalar, and we call this kind of product as the vector inner product. The output of the neuron V is then input to the activation function, that's the phi. The output of the activation function Y is a scalar too. The error E equal to the difference between the desired response D and the activation function output Y. Again, here the E is a scalar too.